Okay. Hello, everyone. I'm recording now. Welcome to the class. Today we will talk about exponentiation. Hold on a second. No, this is wrong. I should, yeah, exactly. So before we do that, we have to talk about number representation and then exponentiation, and we'll see how fast we go and whether the RSA example we'll cover today, because I want it to be done before next week. So if I don't manage to finish the RSA example, I will just post another lecture, and you would have to watch it. Of course, well, you should watch it. I think that it will complement the textbook, but the textbook explains stuff pretty well too. Okay, or maybe better. I'm not sure. Okay. All right. Good. I hope it's complementary. All right. Number representation. So we're all used to decimal system, right? Like we represent numbers with the decimal digits, and we all know how to read this. Alternative is binary, okay, that you might also be familiar with, right? So if the base representation, so here's the base is 10, right? And you have powers of 10, and that's how you interpret these digits. Let's say you're trying to do this in binary. So now you do the same, but with the base 2, right? And because if you have base 10, then the only sensible digits are between 0 and 9. A digit representing 10 would not be needed, because I can represent it as 1 with a 0 rather than, a digit 10, right? So if you're working base B, the digits are from 0 and to B. If you're working base 2, the digits are from 0 to from 0 to B minus 1, right? That's why we don't have the highest digits is 9, not a 10. In binary, the highest digits is the 1, and basically there's only 2 digits, 0 and 1. Okay, and yet, right? So, okay, every number can be represented in any base, right? So base B representation has digits from 0 to B minus 1, and these are elements, by the way, of ZB, right? This is the symbol we use for residues mod B. So base 7, you would use the digits from 0 to 6, and we designate when we write in a particular base, which is not a decimal, we write it with a open close bracket and a 7 in a subscript, right? This stands for 612 base 7. So you know that to interpret the string as a number, you have to do base 7 calculation, right? And so you do that, and base 10, this corresponds to 303, right? So in general, you can represent an integer in any basis, and that representation is unique. Namely, for any n, and for every base b from 2 up, there is a unique sequence ak, a0, a1, to some ak, such that the sequence satisfies these constraints. The leading digits is non-zero, because if it was 0, we can drop it. All these digits are in ZB, and k is the number of these is a non-negative integer, right? So it could be k could be 0, in which case the only thing is here, right? What is b to the 0, by the way? That's a 1, right? Because everything to the 0 is a 1. So this last thing is just a 0. And which ends would you represent with a single digits? These, between 0 and b minus 1, right? That would correspond to k0 and a0 simply equal to n. For any n greater than b, b or greater, we would need more digits here. Okay, so so how do we compute these? Okay, I'm not going to go over this, right? Like this sort of obvious. You compute in the standard way, right? Like so, you just do expansion base b, right? So this is simply this equation here instantiated for a given base, right? So this is instantiated base 6. This is hidden 6 to the 0, right? Which is a 1. This is base 2, right? So it's this string, consecutive powers of 2. Always, my advice, always write these terms, because even though they're 0, so you can omit them, but then you get, unless you write the consecutive powers of 2, you tend to get, I mean, you might get confused as to, you know, have I skipped some powers? No, because, okay, so just, it's better to write it this way, and then simplify and get the proper powers of 2, sum them up. Okay, or base 9. Okay. All right. If there's any questions, you know, just unmute yourself and speak. We are in a smaller group. In a small group, you know, there's only 25 people here, so so you know, it can be more interactive. Bases are arbitrary, right? Like you can have base 37 if you wanted, and your digits would be some symbols that represent numbers from 0 to 36. A convenient base used in computer science is base 16, and this is called hexadecimal basis. And because base 16, well, you need 16 digits. So you have the first 10 digits like so, and then the next 6 digits, well, we don't have Arabic digits, right? Higher, because Arabic system is base 10. So we take just alphanumeric strings, right? Like A, B, C, D, E, F. And how do we read off these things? So base 16, G corresponds to what would be A is 10, B is 11, C 12, this is 13. G is 13. Okay, so 6D base 16 is 13 zeros powers of 16 and 6 first powers of 16. Right, so this simplifies to this, and yeah, okay. I have such a string base 16. Okay, so I write how many digits I have, 3. So I'm going to have 3 consecutive powers of 16. And what are the multipliers? Well, here is an easy one. 1. F is the last digit. So what is it? It's a 15. Yes, because it's B minus 1 and B is 16. And E is one before that, which is 14. Okay, so then the rest is arithmetic. Okay, it stands for this. All right. How do I go? Okay, so if I have anything written in whatever base, the algorithm to compute this in over decimals is clear, right? I just expand it and perform the computation. So no big deal. I know how to compute. Okay, but how about the other way? So you start with a decimal and you want to convert it to base B. Okay, so here's an incredibly concise recursive algorithm to convert an integer base 10, n, into its representation base B, where B is an arbitrary base. The recursive algorithm is this. The last digit of base B representation of n is n mod B. Okay, it's just slash modularly by B, and that's your last digit. Indeed, that makes sense. In a base B, B is so the cyclicity of the last digit is going to cycle every B consecutive integers. You're going to have a 0. So that's exactly the behavior of modular residues, right? You take n mod B, and what you're going to have is cycles from 0 to B minus 1, and then again 0 to B minus 1. So it's the same thing. And then what about the other digits? Well, call this algorithm the same algorithm recursively on n div B. In other words, on the quotient of the integer division of n divided by B. So what you do to find the representation base B is take an n, perform modular integer division, which means get a quotient and get a residue. The residue is the last digit. The quotient is fed into the same recursive algorithm. So now the quotient is the new n. So how do we find the next digit? Well, you told so this is our new n. So we look at that thing mod B, and the next n is going to be that thing div B, and so on and so forth until, and what's the base case? You have a number that is smaller than B. So the quotient is a 0, and you're done, right? Because if n is smaller than B, then this is simply n, so that's the last digit. Okay, so 735 mod 5, you perform integer division mod 5, right? And of course, this is the modular 735 mod 5 is a 0. So because 735 is a multiple of 5, and what multiple is it? 147. You can cross multiply and check. So now, so the last digit is a 0 because of this, and now we run recursively. So let's check. What is this mod 5? It's a 2. So the next digit is 2, and then we do div 5 of 147, right? And what is it? Well, it's 29, right? Because this is almost 150, which is 30 times 5. Okay, so recursively, what's 29 mod 5? 4. So the next is 4, and then 129 div 5 is 5. Okay, yes, 5. Okay, so now basically, okay, we're almost done. So 5 is not smaller than 5. So 5 mod 5 is 0. This is 1, and now we are at the base case because 1 is smaller than the base. So this is simply the next digit. So the answer should be read from this is the highest digit, this is the lowest. So the answer is 10420 base 5. And you should always check. You should perform the easy direction. Compute this, check. This is 0 times 5 to the 0. This is 2 times 5 to the 1. 4 times 5 to the 3. 5 to the 2. No, 5 to the 3, and then 5 to the 4. And compute this and verify that it's equal to 735 because that direction is easy. Okay. Sorry, there should be a comma, not okay. No. This is the power, so it's 625, right? So it's an easy check. This is 735. Okay. Okay, so this is this recursive algorithm. You see it here. Okay, just represented it another way. It doesn't matter. That's the same algorithm. And okay, here is this small algorithm, right? You run recursively on the quotient, and you spit out the modular reduction as the last digit. And the base case is if you are smaller than the base b. Okay, so why is this correct? By induction. If n is smaller than b, then it is correct, right? The n base b is indeed n under this assumption, right? Because n is already in zb, so it's a b-based digit already. In induction, so pick n prime to be n div b, the quotient, and let a0 be n mod b. I call it a0 because this is the last digit, okay, that the algorithm will spit out. So now, if I represent, you know that this is the relation that binds the modular reduction n mod b, the quotient n div b, base b and n. Okay, this is the basic relation between the modular reduction, the quotient, the base, and the integer I start with. So this is true. And now assume by induction that this base b call was correct. So the base b representation of this, that this algorithm returns, is correct. That's the beauty of induction, right? Like we don't have to argue this, we just assume that the recursive call was good. So in that case, this means that n div b, that this base b recursive call returned, is the true representation of base b of n prime, right? Which was the argument called here in the recursive call. So let's say that this correctly computed representation of n prime was this. Now, what do you know about base b representation of anything? Okay, so before we get there, so what is this final call that this guy will return? It's whatever this thing returns, which was that, and added, concatenated at the end, the n mod b, which we call a0 here. So it's going to return this. Now, under the inductive assumption, this stuff is a correct representation mod b, base b of n prime. This equation has to happen, right? Because that's what it means for this string to be a correct base b representation of n prime. So you know this. So by this equation, you can see that n, which is b n prime plus a0, now replace n prime by this stuff with b times this stuff plus a0. And what happens now is that b is going to increment all these powers. So I take b in here, and it now becomes b to the k. And all these other powers the same way, this will become b to the 1. So I have this, which is correct, right? So if a0 to ak is a sequence that satisfies this equation, and each of the ai's is base b, then this means that a0 to ak is the base b representation of n. Okay. So by scrutinizing what happened here, you can basically see that this is correct, that indeed base b representation is a recursive algorithm of just taking modular reductions and modular divisions and recursing on that. That's because, you know, this relation convinces you that this recursion is correct. Okay. Okay. Now, okay. Here is so now without loss of generality, we can go from any base to decimal, and also from decimal to any base. But sometimes there are shortcuts. So if a new base is the old base to some power, then you don't have to do complicated computations to go from one base to another. So for example, so in this case, m consecutive base b strings corresponds to a single base b prime string. Okay, so here is an example that we will care very much, you know, in this class and also throughout your computer science career. Conversion between base 2 and hexadecimal base 16. 16 is a fourth power of 2. So it's example of this for m equal 4. And therefore, this general rule in this case says that for m, which was 4 here, binary digits, in other base 2 digits, corresponds to a single hex digit. Okay? Because, I mean, if you think about this, what is the highest number represented by 4 bits? It is 1 plus 2 plus 4 plus 8, 15. That's exactly the highest power that you can, highest number that is represented by a single hex digit, right? The strings represented by 4 bits are from 0 to 15. And they are also the strings integers represented by single hex digits from 0 to 15. So this is not just for a single digit, for the single, you know, integer from 0 to 15. That's a general rule. Okay. So write yourself a table between binary and hex. Okay. The highest digit is the highest integer is 15, represented in hex this way, represented in binary this way. And then whenever you have, let's say you have a binary string and you want to represent it in hex, okay, group 4-bit segments. So for convenience, just write them with little spaces so that you don't get confused. And now just look up these strings in this table. So 1001 is here, it's a 9, and hex is 9. Okay, you might want to put a leading 0 here, right? Because you don't really have this string 100 here. You have a 0100 here, right? But that's what this represents. It represents a 4. So just by looking up, you know, the hex representation is this. And you can easily go the other way, right? If I give you this, you write yourself a little table and you just find, okay, what is the 4 bits that represent a 9? It's these. What's the 4 bits that represent a 3? This, and so forth. What's the 4-bit strings that represent 13? It's this, and so forth, right? And so you will have a quick way of going from hex to binary and from binary to hex. Okay. A common question: what's the largest number represented that you can represent in base B with certain number of digits? So, so let's say base 8, and I have 5 digits. What's the largest number? Well, base 8, the largest digit is 7. So this is the largest number. Okay, and I can see, okay, this corresponds to this following expression. And now, well, if you remember, this is a geometric formula, right? It's a summation of a geometric formula. It's h to the 0 times h times h times h times h, geometric sequence. If you sum geometric sequence, remember the general formula? You have the factor to the next power -1 divided by the factor -1. Well, that was 7. Why am I not dividing? Because I have actually 7 in front of here. So that's going to that 7 is going to cancel the other 7 in the general formula. and I end up with this. And this makes sense, that this highest number is 1 away from what would be the next number base 8? It would be 1, and all these guys become zeros, right? Because if I try to get like what's a base 8 next number, so I increase this one, I can't. So it's a 0 with a carry. So this I increase, it's a 0 with a carry. This becomes a 0, carry, 0, carry, 0, carry, and I get a 1. So that's exactly this. It's 8 to the 5. It's the next number after that. So you know that the highest number that has 5 digits must be 1 less of this. So you don't have to compute this. You can just, well, there are many ways to remember this. You can compute this and sort of recall the geometric sequence summation, and that this must give you that. Or you think the highest number with 5 digits, base 8, is 1 minus the first number next, which is the 5/5 power of 8. Okay. And the knee-jerk reaction is to just say this, that with 5 digits, base 8 is 8 to the 5, but it's not. It's 8 to the 5 minus 1. And these kind of details will why are we caring about this? Because you have to when you build data structures and you give certain amount of digit places to hold your data, you better know what are the ranges that this thing can stand, right? So that there is no case when you're out of range and the data structure you wrote is incapable of handling it, either throws an error or messes up computation. Okay, so that's the computation I was alluding to. Okay, and in general, if you have base B and P digits, this is the largest number you can represent. Now, converse of this is if I have a number, okay, some decimal number, I want to know if I need to represent it base B, how many digits will I need? So now I need to invert this, right? And rather than compute n as a function of the base and the number of digits, I want to compute number of digit t as a function of n and the base. So I put this on this side and I take logarithms. T is at least logarithm base b of n plus 1. Okay, so, and since t has to be an integer, right? I have to have an integer number of digits. I have to take a ceiling, right? Because this is not guaranteed to be an integer. Okay. So basically, when so it's a logarithm of the base and a number, right? So in order to write a number in binary, I need about logarithm base 2 of the number. In order, how many decimal digits I need base 10 is logarithm 10 of n, right? What's the relation between them? Well, it's the logarithm base law, right? Logarithm of n base b1 is related to logarithm of n base b2 by the following factor, right? So in particular, if you look, okay, log 2, so if I know, okay, this is a quick thing for you to compute, right? If you have a 6-digit number, okay, then of course you can approximate base 10 algorithm. It's between hold on, is it between 6 and 7 or between 5 and 6? It's between 5 and 6, right? Okay, yeah. So now how many bits do you need to represent that number? Well, you take the number of digits it has in decimal, and you multiply by the log 2 of 10, which is about 3 point something. Okay, and that's how you go from decimal digits, number of decimal digits, to number of binary digits. There is a easier approximation, because it happens that the power of 2 that is very close to a power of 10 is 2 to the 10, is very close to 1024 as the third power of 10. So you can also use, gather all the digits of base 10 in triples, and that will correspond to a sequence of 10 binary digits. Roughly, right? Because 1000 is not exactly 1024. And if you convert from, if you know something has, say, 10 hex digits, then how many bits does it have? Oh, well, that one is very clear, because log 2 of 16 is 4. So you simply take the number of hex digits and you multiply by 4 to get the bits, the binary digits, right? Which we already knew, 3 or 4 slides back. Okay, so this is the general law, right? You take a logarithm and you take a ceiling, but these are good to remember, and this change of base, log base law, is basically necessary to remember, to be able to quickly say, okay, I have certain number of digits in a given base. How many digits would it correspond to after change of base? Okay. So now I want to speak about modular exponentiation. It's an algorithm that it's a computation that we'll use in crypto systems. So we actually gave these examples already, but in a context of integer over integers, not modular exponentiation. This does make some differences, but some of these algorithms you have already seen over integers. So here is the basic, the trivial exponentiation algorithm. So what is the exponentiation? It's a sequence of multiplications, right? I take b multiplied x times by itself. If x is 0, then b to the 0 is a 1. Otherwise, I compute recursively exponentiation base b to one less exponent with the same modulus, and I take the result, which is here I denote p, and multiply it one more time by b. Okay, and I do this mod n. So the thing is that this is horribly inefficient, right? So computing a long exponentiation would take you, just too long. We had this algorithm. It was called fast exponentiation, and here was the this was an example of a power of recursion. The base case is the same, but sorry about the noise. There's some work outside of that just started outside of my window. Here, so the recursive call, we compute exponentiation with an exponent that is half x. So x divided by 2, and it's an integer division. right? Because x can be even or odd. And we do this modular n. And then the result, we either square if x mod 2 is 0, in other words, if x is even, or if x is odd, then we take the result, we square it, and multiply by one more b. Okay? So, I can rewrite this, by the way, notice the following. b to x mod 2, if x is even, is a 0, so this becomes a 1. And if x mod 2 is a 1, then this becomes a b. So I can, this is a hidden multiplication of b to the x mod 2. Because if x mod 2 is 0, then b to the x mod 2 is a 1. And this is really also b to x mod 2. It just here that in this case, x mod 2 is a 1, so b to that is a b. So this is a general form of this algorithm that's even more concise. You do a recursive call with half the exponent, and then on the return, you square that and multiply by b to the x mod 2. Notice this is exactly the same recursion as in a representation of a number x in base 2. What did I do in that recursive algorithm that represents any integer base any base? For the case of base 2, it would split x mod 2 as the last digit and then recursively apply the same algorithm to x div 2. The pattern of recursion is identical. You do something x mod 2, and then you do your recursive call on x div 2. So these algorithms would run with the same speed, have the exact same pattern of recursive calls. They do something very different on return. This guy returns an integer and squares it and multiplies by this, right? The other guy just returned a string and concatenated x mod 2 on the return. And yet, in very similar structure. So why is this correct? Again, by induction, okay? So it's the same inductive proof. Look at this, okay? Look at this at your leisure, because it's very nice to convince yourself that this recursive algorithm, indeed, if this call P returns what it should, which is b to the x div 2, then if I square that, I get this, b to the x div 2 square. And if I multiply by b x mod 2, I get it here. And now because it's the same base, so these exponents get added. And this is indeed x, right? This is, recall, it's the basic way of tying together x div base and x mod base is to multiply x div base by the base, add x mod base, and that way you get an x. Right? It's the same equation as a few slides back. Okay, so that's why this algorithm is correct. Of course, the base also has to be correct, but that's a simple fact. Okay. Now, this algorithm is much faster, right? Because how many recursive calls does it make? Well, it's not hard to see that every time it makes a recursive call, it slashes x by a factor of 2. Therefore, the total number of recursive calls is log 2 of log base 2 of x, right? That's how many times you need to slash x by 2 in order to get to 1. Okay. So whereas the trivial algorithm took 1 million modular multiplications to compute this guy is going to take a logarithm of that, which is just 20. Again, that's why is that? Because 1000 has 10 bits. It's 1024, right? So 1 million has 20 bits. Okay, and that's why. Okay, why does it take 2 modes? Here is one, here is another. In fact, this is sometimes vacuous, because if x mod 2 is a 0, then this is a 1, so there is really no multiplication. That's why this algorithm is called square and multiply, because the only operations you do to exponentiate is you square something and you multiply by b, or not even. So it's a series of multiplications by b, and what is this that you start with? It's 1. So in the end of when you envelop the recursion, the first or the last, depends which way you count, p is going to be a 1. So 1 square is nothing. So therefore, basically, you start with a b, and then that b gets squared and perhaps multiplied by another b depending on the bit of x, and definitely square and perhaps multiplied by another b depending on the next bit of x, right? Because here is the this observation that what this thing does, these x mod 2 correspond to bits of x. If I write x in binary, the x mod 2 values that will appear here in recursive calls are bits of x. Why? Because this is exactly the same algorithms that represent x in binary, right? So these things will be bits of x. That is an observation that leads to an in-place version of this algorithm. So if you envelop this this recursion, then you can see it like this: x0 to xn are bits of x, binary representation of x. It's these exponents that will appear here during the recursive calls, because you see the whole way that this algorithm is going to operate depends only on this part. You start with the b, you square it. Whether or not you multiply by b is the whole heart of the algorithm. And that depends on the consecutive bits of x. In fact, when you start from the base of the recursion, you're going to look at the highest, the highest bit, most significant bit of x first, because that will be the bottom of the recursive call. And then the next in the order of from most significant to least significant, the last bit, the least significant bit of x, will operate in the top recursion call. Okay, so you could remove all this recursive structure and just write it like this: if I know the binary representation of x, then I'm just going to go from the most significant to the least and do the following. Start with a 1, because indeed this bottom of the recursion would start from a 1, and square without multiplying by b, because the next bit corresponds to here being 0, which means that I don't do this multiplication, so I'm just squaring. That's this line. Or if that bit is 1, they square and multiply a base b, because that's what this recursive algorithm would do in the case of x mod 2 is 1. So in other words, that bit of x was a 1. Okay, so these are the same algorithms, just viewed non-recursively and recursively. Okay, or I can write it even faster like this. The textbook, now you saw 2 versions of square and multiply. the textbook has a third. Okay, the textbook has a version that is perhaps easier for a human to emulate on a piece of paper. It has more multiplications. These algorithms have exactly at most 2 multiplications per bit. The textbook, the one in the textbook, has more, but it might be easier to operate. Okay, if you were coding, this is what you would do. On a piece of paper, perhaps use the algorithm from the textbook. Okay, it's not substantially different, and yet, for example, the one in the textbook goes from the highest, from the least significant bit first to the highest. Okay, so you know it is a different. I mean, you can see it as a version of the same algorithm, and yet, I guess it's a well, you can call it a different algorithm also. Okay. I mean, because these are the different ones, so these are the ones used in practice. Okay, I guess I'm repeating myself. So, okay, let's try to see, you know, how far we can get in crypto examples. This is the last section of this chapter. Any questions on any of this stuff? Okay. Okay. All right. Let's talk a little bit about the general setting of what we want in encryption, right? So, say, by the way, cryptography is much more than just encryption. If you later take a cryptography class, you will see, or perhaps you already know that, and perhaps you read about it. But the basic thing, the first thing that comes to everyone's mind is secure communication, is encryption. And so that's what we will be giving here as an example. And what's the point? You know, what's the setting of secure communication? So Alice and Bob want to communicate over an insecure channel, and because Eve stands for eavesdropper. So in other words, an attacker who can listen to your communication channel, who eavesdrops on it. So that's why that party is, you know, is abbreviated in this, you know, heavy symbolic biblical Eve term, right? But it really came from just eavesdropper on the channel. So if Alice and Bob need to have some method that allows Alice to convert her message into a cipher, so encoded in some way using a key, and what she will transfer over the public channel is that cipher. The cipher has to have the property that Bob, having a decryption key, perhaps the same one as the one Alice used, perhaps a different one, that would allow him to decrypt, right? And the encryption and decryption algorithms have to have the property that if I encrypt and then decrypt using a matching key, I get always the same message. But for security purpose, right, it also has to have the property that somehow the cipher to someone who doesn't have the key, who perhaps can search the key space for the key, but the key space must be large enough so that that search is infeasible. That person has no faster ways to no shortcuts to decipher the message from the encryption, apart from the trivial brute force attack of searching over all possible decryption keys, applying them to the message, and just seeing whether the decryption makes sense, and therefore it's likely to be that this guy just got lucky and found the correct key from the large search space. So first of all, we have to encode messages into numbers, right? Because our crypt system will work over numerical structure, namely modular residues. Okay, to be precise, right? Like, so the RSA example that we'll dive into will be working on modular residues. So you have some text. How do you encode it as, say, modular residues, right? But we already know that, because say that you have a text and you encode it in ASCII, right? So ASCII is an encoding where every character is encoded with 2 digits. So you have the string. Okay, these are concatenated digits, and now represent this in okay, and on the way back you decode it, just by decoding ASCII. But what's non-trivial, right? Once you get so our crypto systems will work on modular residues. For some large integer n, you need to encode your messages as an element in the n, in order a digit base n. So you have this thing, and now you need to represent it as a bunch of strings base n. Okay, so you just use the algorithm we know, right? Because this is some very large integer, but you can convert it to base n, using the same process as we were given, right? So how many digits do you need? Okay, if base 128 you had n digits, then base n you will just translate by this factor. Okay. So we will not, this is just for your info, okay? You can convert alphanumeric strings and think of them as integer strings, mod some base. Okay, that's the base used in ASCII. And you can convert that to an arbitrary string of base n elements for whatever n is needed by the crypto system. And you use everything that I was talking about before. Okay. We will not, be like asking you to run these algorithms, during a test. It's not particularly illuminating, okay. But you should know that's still like roughly how how this would be done. But after this, we'll just think of an encryption and as some function on this field of modular residues. Okay, and both encryption and decryption will be functions like this, but both of them will have an additional input, the key. By the way, it is not absolutely not necessary. Not every crypto system works like this. For example, there are crypto systems using lattices. The lattices, the plaintext and ciphertext in those crypto systems are vectors over some space, which often is, which is actually this. It could be an extension field, which means that these are polynomials, but it's still over. You can represent it as just a bigger dimensional vector over some space like this. Sometimes n it would be a prime for some crypto systems. For others, this could be a power of 2. because it's convenient for encoding and as a fast computation. For RSA, this is neither power of 2 nor a prime. We'll see soon what it is. It's a composite, a very special one, a product of 2 primes. So it is not, completely general, and yet essentially the case for almost all crypto systems we know. Okay, here is a toy crypto system called a shift cipher. That crypto system is called simple encryption in this chapter. So it's not called shift cipher, but in cryptography it is known as a shift cipher. Okay, and I will talk about certain generalization of this as well. Okay, this is how shift cipher works. Let's a key. So for a shift cipher, we need to settle on the modulus. Let's say modulus is 79. A key is the random number in the modulus. So in other words, in Zn. Okay, so it's a number between 0 and 78. Let's say that the key was 55. Encryption, it works like this. If a message is encoded in Zn, okay, so it's a number in Zn, then encryption is just taking this message and adding the key mod n. Decrypting is taking the ciphertext and subtracting the key mod n. And note, for every key, this encryption function is a one-to-one and on-to function from Zn to Zn, right? So it's one-to-one because if I take 2 messages, 2 Zn numbers, and add the same integer to it, I get different number from Zn. In fact, that's because the inverse function exists, and this is the inverse function. Okay, so it's rather immediate that this encryption scheme is correct in the sense that for every key k, for every m, if you first encrypt and then apply decryption to the result of encryption, you get m back. Because see, if m plus k mod n, if I subtract k, then mod n, I just cancel this k, right? And I get m out. So in this case, if k is 55 and message is 41, I add, so I get 96, but because I do mod 79, this is 17. And if I decrypt, you can check that 17 minus 55 mod 79 is 41, right? So, okay, of course, you cannot do this memory, but it will be. Here, when the same modulus message is 41, key is 13, I don't have a wraparound. I simply the sum over integers is smaller than the modulus, so that's easy. Okay, okay, so here is the shift cipher. Some properties of it. Note that if you have a single message ciphertext pair, then this basically reveals the key. Because given a single m and a c, and knowing the modulus is public, everybody knows what this modulus is, okay? Because you cannot hide this. People can see that the numbers that are sent are, like between 0 and 78. Okay, so they know that the modulus you're using is 79. Because there is a single solution to this equation when I give you C and M. Just put M on this side and you're gonna get the K. And that's what happens here, right? So if you compute key K in this way, that's a correct key. So a single usage of this, that's why it's a toy crypto system, because the single usage of it if the attacker guessed like what the message was. So, for example, you encrypt. The first message you encrypt is hello. Then the attacker immediately gets a hypothesis what the key is. And if you use the same key for any next message, then the attacker will decrypt that. Okay. Another thing that this now, how likely is it that does an attacker only see ciphertext? Why should he have this message so that to be able to compute the key? Well, so that's the cryptanalysis, failure, right? In both Second World War, in both attacking the German ciphers, and also that's how Americans decode the Japanese ciphers. They guessed what the beginning messages were. That there would be some predictable messages sent at the beginning, a date, some fixed format. And once they had the hypothesis on what that is, they just cycled over possible hypotheses, and then the one that stuck allowed decryption of the rest of the message. Repeat. Well, also, a single ship with the machine tells you what the plaintext is, and then you know the format. Repeat in plaintext also means repeat of ciphertext. So if you encrypt this way, then the same plaintext M will be encrypted always the same way. So if you apply it to encryption of text, like these ASCII symbols, and you simply encode every digit. Let's say the modulus is 128, so simply the modulus matches the ASCII encoding. Then every ASCII string will be mapped to the same. Then every occurrence of a certain ASCII symbol will be mapped to the same ciphertext using this encryption. So that's not great, because then you can use frequency analysis. You see the most repeated letter, and you guess that this corresponds to. This allows you to recover of the plaintext. Okay, so I'll show this in a few slides ahead. So Caesar cipher is it's a simple. It's an example of a shift cipher with fixed shift 3, and a shift cipher just generalizes it to an arbitrary shift. Another reason why this is completely insecure is that for small moduli, you will be, and the moduli have to be small because you cannot, for speed of encoding. So if you, for example, use it over alphabet, so your modulus here is 26, and because your digits are the digits are just integers between 0 and 25, you have 26 digits. So this is the shift cipher over Z26. The key is a random number in here, yes, and there is only 26 key possibilities. So you just decrypt under every key, and if you have a long enough cipher, then you can you get plaintext hypotheses for every key, and you just check whether the decryption corresponds to a sensible English words or Japanese words or whatever. You can decode every language in that way and just compare it to some publicly available strings in that language. Here is a generalization of the cipher. Rather than simply the key that encodes a shift, okay, so an additive shift between, if A is mapped to C, that means the shift is of 2, so then B would have to be mapped to D, and C would have to be mapped to E, etc. Well, why not consider a general permutation between letters? In other words, any one-to-one and onto function from Z26 to Z26. Okay, And the key is just this permutation. So it's a lookup table. It's not very large. You just have to write out 26 letters in some arbitrary order, and that's your key. So it's not a large key. I can share it. Alice and Bob can create it and share it. And they encrypt by just looking at the text and encoding the text, in this way, and applying this permutation function to every letter separately, just like you encoded, in English sentence using a shift cipher, or you took individual letters and you used the shift cipher encryption on them. So here the search space is no longer so tiny, because the key is there's not just 26 possibilities, there's 26 factorial possibilities, right? Because how many reordering of 26 letters are there is 26 factorial, right? 26 possibilities for this, 25 for that, 24 for that, And 26 factorial is a large number, so you cannot brute force search it. But still, it has the same property. The occurrence of the same letter is going to always appear the same way in a ciphertext. So here's how the frequency analysis works. You look at the letter and you see, okay, you know that in English alphabet, and that's true for every language, certain letters have much higher frequency than others. In English, the most frequent is E, and you can get tables of these frequencies on Wikipedia. And so diagrams, so pairs of letters have known frequencies, right? And so, for example, PH, AN, IN, these are the common repeated diagrams in English. So when you have a long text, you just count, and you see that the ciphertext string B, has the highest occurrence. So you guess that this corresponds to the highest frequency letter, that B must be an encoding of the highest frequency letter. Your natural guess would be that N is the next frequency letter and T is the next frequency, but maybe that choice, didn't correctly correspond to sensible decryption. So you vary, you search over this flexible search space where, okay, so you make another guess. How about making this the next frequency letter, right? The exact way that you search is, okay, it's a kind of a cool programming exercise. But still you can see that you will do best fit between frequencies that occur in your text, in your cipher, and the frequencies that you know from Wikipedia of English letters. And then you will do the diagrams, the trigrams, and you can use generic best match algorithms to solve that puzzle quickly. Okay, so it's a ciphertext only attack. And even though this particular version works for English text, but it really works for every language, right? Because of the same, irregularities that are present in every human language. It also works for other message spaces, right? Because they also have irregularities. Like if you look at HTML messages on the web, or IP packets, they're not random bit strings. They have quite predictable structure. There's a lot of patterns that are well known, and if you use any of these ciphers, you would break them in a corresponding way. So key size is not a guarantee of security. You need something else, and this is where modern ciphers come in. DES, whose keys are 56-bit strings. So there is rather large search space, although not enough for modern computers. So this has been replaced by something we call triple des, which basically has 3 such keys, and this is phasing out, and there is the modern crypto system that won a bunch of basically competition to be a des replacement. AES. And there is many others, but this is the current de facto standard. So will it be sensible for me to talk about RSA right now? I think maybe not so much. Let me check how many slides I have. You know what? Maybe not so much. So you know what? Let me do that. I will post this. I'll post a link to, or I will just continue, right? So if you have to go, you have to go, but you can tune in on YouTube later and just fast forward. So let me go to this. I'll just continue with my RSA presentation. Where am I? Hold on a second. Okay, here. Okay. By the way, do you have questions to any of this previous stuff? Okay. Okay, so let me go over the RSA example. The shift cipher and even DES or AES are examples of something we call symmetric crypto systems, where the two communicating parties in advance agree on a secret key. There is an alternative to doing stuff this way. It's called public key cryptography, where when, for example, Bob, the receiver in this scenario where Alice sends a message to Bob, creates a pair, something we call an encryption key, which we call public key, and decryption key, which is a private key. So when he generates his key, he doesn't generate a single one, he generates a pair. And the public key he can publish. And therefore Alice, and in fact everybody in the world, can know it. There is all sorts of practical problems in key distribution. How do I know that this is really Bob's key? But that we'll leave off for now. That's the job, for example, of public key infrastructure and certificates. But if Alice has Bob's key, then the encryption function will take as input the public key and a message and produce ciphertext, while the decryption takes ciphertext and a private key, denoted SK, like a secret key. So the RSA crypto system is an example of an encryption procedure that we call that is an example of the following paradigm. The encryption function is some function keyed by a public key, and that function is a function from message space to ciphertext space. In the RSA case, both of these would be modular residues mod n. Okay. The reverse, because this will be a one-to-one and on to function. So it's for every public key, this will be a permutation. Okay, so it's invertible. In the case of RSA, it will be in permutation because the plaintext and ciphertext live in the exact same space. So there will be an inverse function, okay? Let's call it G. It's a function that maps ciphers into messages. G is the inverse of this is a decryption function. And now, if the public key is public, then this function everybody can compute, right? In the what we call forward direction. Given a message, I can compute this function forward, compute the plaintext, the ciphertext. This has to be an efficiently computable, or otherwise encryption will not be efficient. But in order for decryption to be hard against this eavesdropper, remember this picture? Alice here, Bob here, and they send a message and hear the big ear that listens. Well, that ear is gonna get the output of this function on plaintext M. So the inverse function that takes the ciphertext and computes the inverse of the function, right, must be hard to compute, given only the public key. So this is something we call one-way functions in cryptography. That I describe this function fully. You have the public key, you know the moduli, so you know what the domain and the range are. You can compute this function, this forward direction, easily, but the inversion seems like a hard problem. Okay, but there is also something else has to be true, that there is some private key that can be generated that would work like a trapdoor to this inversion function. Without this trapdoor, the inversion function is hard to compute, but once I give you this trapdoor, which is the information Bob stores, then there is some efficient way to compute this otherwise hard to compute function G. And that's the legitimate decryption. That's what RSA cryptosystem is an example of. It's a public function from Zn to Zn, which without the trapdoor, secret trapdoor information, we don't know how to invert it. And that's the basis of RSA cryptosystem security. But there is a hidden trapdoor that the Bob can create together with creating his public key. That's the decryption key he will keep close at heart to his heart. And if that doesn't leak, he will be the only one who will be able to apply the decryption function, to compute the decryption function efficiently. Okay, here is the RSA cryptosystem. When you pick a key, the public-private key pair, you have to pick two primes that are both very large. They're in a modern RSA, what's recommended is that these primes are at least, each of them is at least 1,000 bits or even 2,000 bits. And what you do with them is you multiply them. That's the modulus that an RSA cryptosystem will use. It's a composite, and it's made of multiplying two very large primes. If these two primes are 1,000 bits each, the modulus is 2,000. If these two primes are 2,000 bits each, then this is 4,000. This is abbreviated as 2,000-bit RSA or 4,000-bit RSA. Okay, different levels of security of a cryptosystem. In addition to multiplying them, you also compute the special symbol phi, which is a product of these P and Q, but decremented by 1. So it's a product of P minus 1 and Q minus 1. Next, you pick a small prime, E, which is co-prime with phi. Okay, you use the Euclidean algorithm to check. In practice, RSA is most commonly used for a very small prime. In fact, it is the first small prime that is not even, right? I mean, the smallest prime is 2. And why is not 2? Because if P and Q is prime, then they are odd. So P minus 1 and Q minus 1 are even. So 5 is even. So 2 has no chance being co-prime with 5. But 3 could be. So in practice, we pick E3, we fix E3, and we pick primes P and Q, so that to make sure that neither P minus 1 nor Q minus 1 is divisible by 3, so therefore 5 has no 3 factor, so therefore it's co-prime with 3. And okay, finally, we compute D, which is a multiplicative inverse of E mod 5. All this business about using extended Euclidean to compute multiplicative inverses will in particular kick in right here. It's a crucial step in RSA key generation. You need to be able to, you generate this very large modulus, n, let's say 2000 bit, phi is also 2000 bit, okay? Maybe it's 1999, yeah, because we're multiplying slightly larger number, but only slightly. So this is a large, instance of extended Euclidean algorithm to run this, to come up with these two coefficients, if you remember. And one of these coefficients will be the multiplicative inverse of E mod 5. How big will this inverse be? Well, if this thing has 2000 bits, then it might have 2000 bits. Okay, and the multiplicative inverse has this property, right? That inverse multiplied by E mod 5 give you a unity. That's the definition of multiplicative inverse. And the public key is a pair of the exponent and the modulus. The private key is this G. You don't have to remember phi. You used it to create this exponent, this value D, but you can discard it after generation. Now, people often think, so the basis of RSA security is hardness of factoring in the following sense. If you know how to if there was an efficient factoring algorithm that in particular worked efficiently on integers that are created as products of two large primes, then that algorithm would give you, given the public key, the modulus n, I would feed it into the factoring algorithm, I would get P and Q, I would compute phi, I would run the extended Euclidean to compute D, and I would have the private key. So factoring must be hard for RSA to be secure. Unfortunately, we don't know that this is if and only if. So it might be that even if factoring is hard, RSA is nevertheless broken. But we don't know of any other breaks. So the only way to break RSA we know of is to break factoring. So best attacks against RSA, and that would in particular tell you that for modern computers, you need the you need the modulus n to be 2000 bit long, or perhaps even 4000. That's because the best factoring algorithms applied to such numbers are estimated to run with roughly 2 to the 122 steps. So 2 to the 128 steps, right? So they will have 128-bit security based on that. These are estimates, but it's by strength of the factoring algorithms that we estimate this is the strength of RSA. Okay. Okay. So this is what the secret and public key is. Now, the message space of RSA is not exactly all the modular residues mod n. It is only a subspace of these modular residues, which we denote Zn star. It's the subspace composed of those residues which are co-prime with the modulus. Now, if n was prime, then all integers in Zn will be co-prime with n except for 0. But if n is composite, this is not true. Remember, n is a product of two numbers, p and q. So, for example, p is smaller than n, so therefore it's in here, but p is not co-prime with n is p times q. So multiples of n of p and multiples of q, multiples of either of these primes, would be outside of the message space. However, finding these multiples is equivalent to factoring. So if you find me a message that I cannot encrypt with RSA, you break RSA. So therefore, in practice, it doesn't matter. You know, finding these X which are in here but not in here is just as hard as factoring. But for small examples that you will work with on the homework and on the test, you will need to know the difference, because you know, if your messages are in the wrong space, namely they are not co-prime with the modulus, then RSA will just fail. Okay, it will not, and you will quote unquote encrypt them, but decryption is going to fail to invert the encryption. Okay, so that's the message space. And now encryption and decryption are sort of simple. So you take a message to encrypt and you exponentiate it to this exponent e mod n. Decryption with a secret trapdoor d, which is you know, has this relation, is works similar to encryption. You take a ciphertext and you exponentiate it to power d. So boom, that's why you know, we wanted fast exponentiation. I mean, that's not the only example where we need fast exponentiation. In fact, we need it for you know, many other crypto systems. But here it is in the case of RSA, right? Both encryption and decryption are exponentiations. You don't need a complicated exponentiation algorithm when e is 3, right? Because this is just m times m times m. But d is a very high. D is if phi is 2000 bits, d has 2000 bits. So this will be a square and multiply with a 2000 bit exponent. So it will run this recursive loop 2000 times, right, to get down to the base case. And how many squares and multiplies it will perform? 4000, right, at most. Yes, because it just does 2 times the number of bits. So there is a big efficiency gap between encryption, which uses 2 modular multiplications, m times m times n for E3, which is commonly used, and decryption, which used maybe 4000, right? That is a huge gap between efficiency of RSA encryption and RSA decryption. That could work to your advantage in some crypto systems where maybe the imbalance is great. Perhaps we encrypt stuff a lot and decrypt less so, like a log, you know, is a good example. You write stuff all the time and you read them occasionally. Also, you know, if you set this correctly for client and server, you know, a small smart card and a laptop, etc., etc., you have power imbalances all over the place in computer applications. But there are other crypto systems that are balanced in this way, and right, and they might be preferable in some applications as well. This is my the very rich slide, but your question here should be, okay, security, whatever, right? We don't have. I mean, I told you, like, it's based on these principles, based on factoring. It's also that this cubing function, which is the public key encryption function, is believed to be one way. So whereas I can cube, nobody else can compute the third roots to invert unless they are given this solution to this equation. Now, but why is this correct to begin with? Why is this inversion? Why is this function really an inversion of this one? That's because of this equation, but it requires some looking into. So now, this is called Euler's theorem. It's that as long as, for any modulus n, if you have an integer that is coprime with the modulus, then there is a fixed number called phi of n, such that this number exponentiated to phi of n, mod n gives you a unity. That phi of n is a number of elements in Zn which are coprime with n. In other words, a number of elements in Zn star. If n is a prime, then this number is simply n minus 1. That's because all elements in Zn are coprime with n if n is prime, except for 0. That's why it's not n, but n minus 1. If n is an RSA modulus, in other words, it's a product of two primes, then that magic number is p minus 1 times q minus 1, which is exactly how phi is computed in RSA cryptosystem. Because what it is really is the case of this general Euler's theorem for the case of n, which is a product of two primes, where this thing becomes p minus 1 times q minus 1. Now, one consequence of Euler's theorem, the fact that if you start with any message and exponentiate to this phi, p minus 1 times q minus 1 in the RSA case, mod n, you get a unity. A consequence of this is that if you exponentiate numbers to any exponent, and you use a modular exponentiation, you don't have to perform this exponentiation for the whole exponent x. What you should do first is to modularly reduce x mod phi. This is true. Why is that? Because what's the relation between x and x mod phi? X is x mod 5 plus some multiple of phi. But so therefore m to the x is m to the x mod 5 plus some multiple of phi. But m to the multiple of phi is the 1. So that part of exponentiation cancels out. And you only get this. So that's why this is true. That implies that if you chose ED to be 1 mod phi, then the following is the case. If you take C to be ME mod N, which is the RSA encryption, and you take the ciphertext to the D, which is the RSA decryption, then watch what happens. C is ME mod N. Because I compute mod N, so I can skip this internal mod N and just save it to the last. So C to the D is the same as M to the E in bracket to the D. Now, by laws of exponentiations, it's the same as M to the product of ED. And because I'm exponentiating mod N, where exponentiating to the phi is like a 0, is like exponentiating to a 0, I know that M to the ED is the same as M to the E mod phi. Consequence of Euler's theorem. And because I set ed mod phi, I set the RSA decryption key to precisely satisfy the equation that encryption exponent times the decryption exponent are 1 mod phi. So therefore, this expression is 1, and so m to the 1 is the m. So that's why this expression guarantees that if you take anything that is in the message space and encrypt it, and then somebody takes, the recipient takes that and decrypts it, then the result comes back to be m. Okay? And you have to start with something which is coprime with the modulus, because only then this theorem is guaranteed. Okay. So this implies the correctness of encryption. Let me finish with one example. I take P5 and Q11, the 2 primes. My n is 55. Phi of n is P minus 5 minus 1 times 11 minus 1, so 4 times 10, 40. If E is 3, so I checked this correctly. The 40 and 3 are coprime. I can compute this multiplicative inverse of 3 mod 40. It happens to be 27. You compute this by extended Euclidean, but you always check. You check that you don't take it, at a face value. Maybe you made a mistake, but checking is easy. Multiply 3 times 27. It should give you a unity mod 40, and indeed it does. 3 times 27 is 81, which is 1 mod 40. Okay, so the public key is the modulus, which is 55, and the exponent E, which is 3. And the secret key is 27. This inverse modular, the multiplicative inverse of E modulo this secret modulus phi. The message space is all integers here, which are coprime with 55. So we enumerate the integers, but we kick out multiples of 5, and so there's no 10. Also kick out multiples of 11, right? We have to kick out all multiples of factors of 55, so multiples of 5 and multiples of 11, right? How many of these integers there are? 40. Okay, and you can see that this will be true. It's how many do you kick out? 15. There will be 5 multiples of 11 that you kick out, and 10 multiples of 5. Okay, and they are, or 11 multiples of 5 and 5 multiples of 11. 11 plus 5 is 16, not 15, but there's one multiple that is overcounted, the 0 multiple of 5, and a 0 multiple of 11, which is the same number as 0, which is counted twice if I count this way, right? So that's why it's it comes out correct. All right. So these are the encryption and decryption functions. And let's say we test it on message 17. It's in the space because it's not coprime with either. It's not divisible by 5. It's not divisible by 11. Encryption takes 17 to the 3rd power mod 55. Okay, so it's 17 squared times 17. So 17 squared mod 55 is 14, right? You just make a table, multiply this and reduce mod for 55. You're gonna get 14, and this multiplication mod 55 is 18. Decryption is a more complicated thing, right? Because so you take 18 to the 27, because why 27? The decryption exponent was 27. we want to write this using square and multiply on a piece of paper. So the easiest way to do so on a piece of paper is write 27 as the powers of 2, and use square and multiply basically like this. Now, 18 to the 16 is 18 to the 2 to the 8. 18 to the 8 is 18 to the 2 to the 4, and so forth. And now, compute these inner values. So this is 18 squared mod 55, happens to be 49. So now I can replace both of these by 49, and this one, and recurse, because now, okay, so now this is 49 squared to the 4th, and this is 49 squared to the 2nd, and this is 49. So I compute 49 squared, happens to be 36. And so on. I recurse in this way. Right here, I will have 36 square computed. So that happens to be 31. Finally, so if you see what I'm doing, I'm compute the stuff that I need to compute on a piece of paper next to me, right, is 18 square, then 49 square, then 36 square, and I'm done with squares. And 31 square. And now I'm done with squaring, and I do the multiplications. And these I have to do by hand. This is not the reason that this is anyway. It's a form of square and multiply, but actually it's slightly different than the one I was giving you earlier. This is the one that is in the textbook. In the computing on larger moduli, even like 55, okay, it's not easy by hand. You would have to, compute this and then do a modular reduction. It takes a bit. So the examples I will give you will deal with smaller moduli, not smaller primes like 3 and 5 or 5 and 7, okay, or something like this. Okay, that's all I have. If you have some questions, please ask them. And now I'll stop recording now. And okay, so take care. Watch out for the homework and exercise example in the textbook. Have a good weekend. Bye.